Lecture 6, Process Selection and Facility Layout. So we're going to talk about the process selection, the types of processing, the need for layout and planning, the process strategy. We'll talk about facilities layout, and then we'll actually do line balancing example. Process selection and system design. So there's a lot of considerations here. So you have capacity planning, and that's interrelated with process selection. So how much capacity do you need? And then you design the processes around the capacity. Going into this, you have forecasting, you have product and service design, and then technology. Technology can change things. Coming out of you'll have facilities and equipment, you'll have a layout, and you'll have work design. So there's different types of processing. So this is comparing 4 different types. The first is a job shop, and this is like you might call like a auto repair shop, where the people come in and it's very specific jobs. It's very customized. You can handle a wide variety of work. You come in, might need an engine rebuilt, you might need a tune-up, you might need your brakes adjusted, you might need new tires. The disadvantage of this is it's slow, high cost per unit, and it's complex planning and scheduling. So the next is something called a batch, and this is where you have semi-standard goods or services, and you do a whole bunch of the same thing. And the advantage of this is you have flexibility. It's easy to add or change products and services, and the cost per unit is a little bit better than the job shop, and you have moderate scheduling complexity. And then the next one is repetitive or assembly line. This is where you have standardized goods and services, and you're just doing the same thing over and over and over. This might be building an automobile, building furniture, different things like that. Low flexibility, high cost of downtime. So you have this assembly line, and when it goes down, everybody in the line is waiting for that one piece that's going down. And then continuous. This is highly standardized goods or services. It's very efficient and very high volume. It's very rigid, lack of variety. It's costly to change and very high cost of downtime. So those are the types of processing. So why do you need to plan for layout? The first is, if you don't plan, you're going to have inefficient operations. You'll have high costs, you'll have bottlenecks. If you have a poor layout, you could also have more accidents or safety hazards, people tripping over each other or tripping over equipment. When you change the product or service design, you may need to change the layout. When you introduce new products and services, you might need to change the layout. When you change the output or product mix, where you're going from low volume to high volume, or maybe high volume to low volume, the layout could change. When you change methods, you change equipment. And then the environmental or legal requirements, everything's working great, and then there's a new law where you have to do something different. Maybe it's OSHA, it may be pollution or something like that. And then morale problems. You want to keep the employees happy, and sometimes just changing the layout will make their job easier, make them happy. So the design objectives, the basic objective is you want a smooth flow of work, material, and information through the system. So it goes from station A to B to C. And then some of the supporting goals is you might get better quality. You use your workers and space efficiently. You avoid bottlenecks. You minimize the material handling costs. So if you're constantly moving things around the room or between places, that's going to cost you money. Eliminate unnecessary movement of workers or materials. So if a person has to keep walking back and forth when you could just move what they need closer to them, or the material, if they need the material, move the material or move the material to the next station. Minimize production time or customer service time, and also design for safety. So the first one is something called repetitive processing or product layouts. So a good example of this is if you go to Chipotle, Dos Bros, or one of these places where you're walking through the line, ordering as you go. So if you go to one of these places, the first thing they ask is, what do you want? Do you want a salad? Do you want a burrito? Do you want a taco? And that first station, they may cook your burrito shell, warm it up, ask you whether you want rice or beans or meat. And then you get to the next station where they're adding in some vegetables, salsa, guacamole, lettuce, tomato. The next station they might ask you, do you want a drink? What do you want there? You use it for here to go. They give you a basket, they put it in a bag, and then the final station you're paying for it. And what will happen is sometimes during low periods, one person might be doing station 1 and 2 together, and the other person's doing station 3 and 4 together. Or even in really low times, one person's doing all 4 stations and the other person may be in the back cooking. So that's an example of this. You add things as you're going through the stations. And this can be used for repetitive or continuous processes, although the example I gave is really customized. So non-repetitive process layouts, this is where it goes slightly different. So in this case, this is intermittent processing, maybe a job shop. Something comes into Department A and it goes around and leaves at Department F. So a good example of this might be registering for a class, maybe this class. You might have to go to financial, you might need financial clearance. You might need to talk to your advisor, you get your textbook, register for the class. Those are like different departments, different functions. But you might go through it in that order, where another person might start with their advisor and then register for the class and then get financial clearance. And they end up doing it in a different order. And then you have another person doing it very different. And so it allows variety. It allows a slightly different order. So this is a process that's non-repetitive. Fixed position layouts. This is where what is being worked on is in a fixed place and the workers, materials, equipment are moved as needed. So here's an example of a dam. So dam needs maintenance. The workers there, they're moving around the dam to maybe do painting, they may be doing inspecting, they may be repairing the generators that generate electricity, but the people, workers, equipment all go to whatever piece of the dam that needs repair. On a ship, to repair the ship, the people go to the different stations on the ship to repair what needs to be repaired. And there's combination layouts, and this is an example where, like a hospital. So a hospital, as an outpatient, you may go you check in at the hospital to be admitted, and then you go get your blood drawn, you do a couple of tests, and then you're done. You're moving like from department to department. Where another case, you might come into the ER, and rather than moving from department to department, someone will come into your room and admit you. They'll come in and draw your blood instead of going to the lab. Some cases, they'll actually bring the x-ray machine into the office. I fell down while roller skating a while back and had a bruise, so I decided I better go make sure I didn't have any problems. I went to the ER, and instead of them taking me to the x-ray machine, they actually brought the x-ray machine to me and took an x-ray right there in the room that I was in. So you have these combinations. A supermarket, in some cases, the meat could be taken to the meat department to be processed, or other cases it's prepackaged and taken someplace, shipyards. Then some organizations are moving away from process layouts to things like cellular manufacturing, flexible manufacturing systems. Service layout. So you can think of service layout characterized as a product, process, or fixed position. So service layout requirements are somewhat different due to factors such as degree of customer contact, degree of customization. So common service layouts, warehouse, storage layouts, retail layouts, office layouts. An example is getting your oil changed. Some places you go drop off your car, you go into the waiting room, and then they take your car, they change the oil, and then come back, and that's it. There's some of these quick shops where you drive in, you stay in the car. Some places will hand you a newspaper. They're asking you questions. You're just sitting in the car. They're changing your oil, and they're done with you just sit there, and you never get out of the car. And in like the 10-minute oil change, 10 minutes, the car's done, and you drive out. That's an example of a different kind of a layout. It's the same bay, but it's a different sort of design of the service. Line balancing. So line balancing is the process of assigning tasks to workstations in such a way that the workstations have approximately equal time requirements. So our goal is to have equal time requirements. So why is this important? It allows you to use labor and equipment efficiently, and you avoid fairness issues that arise when one workstation must work harder than the other. So we'll go through a little example. Cycle time is the maximum time allowed at each workstation to complete its set of tasks on a unit. So this establishes the rate of output. So cycle time is equal to operating time per day divided by the desired output per day. So the output is equal operating time per day divided by the cycle time. So let's see how many workstations are required. So the number of workstations is a function of the desired output. So there's a theoretical number of workstations, and that is if you take the minimum number of stations and you sum all the task times, you can come up with this theoretical minimum number of stations. So here's an example of a precedence diagram. And in this case, this is an example of positional weight. So here you have 0.1 plus 1 plus 0.5, and 0.2 is equal to 1.8. So in this case, this is the positional weight is 1.8. If you look over here, this one, you add these two together, it's larger than this one. So that's sort of the precedence diagram. So if you're worried, do I need to get started on this one first or this one? You definitely want to start with this one first, because you can get started with this, you can start working on this, and then the guy shows up and starts working on this, and then they show up at the same time. So you essentially have about 0.4 minutes of reserve on this one. So here's an example. A manager wants to assign tasks to workstations as efficiently as possible to achieve an hourly output of 33 1/3 units. Assume the shop works a 60-minute hour. So assign the task shown in the accompanying precedence diagrams, the times are in minutes, to the workstation using the following rules. In the order of the following in order of the most following tasks, and the tiebreaker is the greatest positional weight. And then the second question is, what is the efficiency? So let's start with this. So if you say the order of most following tasks, this one has the most following tasks of everybody behind it. This is the second most following tasks. And then these have a tie on the most following tasks, but then it's their greatest positional weight is these two have a higher positional weight than this, because this is going into a shorter task than this. So the positional weight of these two is 1.0 plus 0.5, where the positional weight of this is of these is 0.5 and 0.5. So let's start working out. So the first thing you do is how many minutes are allocated to each workstation. So that's the cycle time. It's 60 minutes divided by 3.33 units. It comes out to be 1.8 minutes. So a workstation can't take any more than 1.8 minutes. So you begin allocating tasks to workstations. So remember, you start with the order of the most following tasks. So you start with this workstation. And so there's 1.4 minutes. And then you say, well, can I combine it with the next one? And here you have 1.4 minutes and 0.5 minutes. You add that together, that's 1.9 minutes. So 1.9 is greater than 1.8, so you cannot combine these two positions together. So the workstation is this. Now you start with the next one, and you look at this greatest positional weight. This one is not the greatest positional weight, so you start here. This one has the greatest positional weight, so you add these two together, which is 1.3, so you still have 0.5 left. So could you combine it with either of these? And the answer is no, because if you combine it with this one, it would be 1.9. So then you keep going down here, and so I've done the rest of these. You start, this has the greatest positional weight. You can add this one onto it. You can't add this one, but you can, you can add this one, but this has greater positional weight. So you add these together, and you can still add this one. And then these two are together. So you add up the station task times. So the first station only does A, the second one does B and E, and you add that, that's 1.3. This station is C, D, F, and this station is G, H. So given this, if you're lazy, which station do you want to work at? You want to work at station 2. So that one, you get a little bit of time. You get to goof off a little bit. You have some free time. This is the station 1.8. You have no spare time here. A lot of times, if you work in an area where the new person gets stuck on here, and then when someone finally quits, and the most senior person gets stuck here, it gets to go here because this is the easiest one. So the new person is working really hard. The second newest person might be over here. The third newest person is over here, and the most senior person here. That's in a shop that values laziness. If you're really valuing efficiency, you might actually put the most experienced person here because they may be able to do it. They've done it so much, they may be able to do it in 1.7, 1.6, and you can actually increase the output. But in this case, we're just assuming everything is the same. And this is why you want them to be as close as possible so that you don't have fights over which station they're on. So the next question was, what is the efficiency? So the efficiency is 100% minus the idle time. So the idle time per cycle, if you look at this, you essentially take 1.8 minus whatever the time was. So you add those together. Station A is 1.8 minus 4. And you add all of these together, you get 1.2 minutes of idle time. So the percent of idle time is the idle time per cycle divided by the actual times the cycle time. So it comes out to be 16.67% idle time. This is the cycle time calculation. We already did that. So the calculated cycle time actually equals the actual bottleneck station time. So station 3 is the bottleneck, and it uses all 1.8 minutes. So had that been, say, 1.7, then you could actually get more done than the target. So the efficiency is 100% minus 16.67%. So that's 83.33%. So here's a summary. We talked about process selection, the types of processing, the need for layout planning, the process strategy, facilities layout, and then designing product layouts with line balancing.